This is AP Calculus Practice Exam 1. In Part 3, we will finish up the multiple choice, no calculator section. If you haven't seen Part 1 or Part 2 yet, you should definitely watch that first. Either click the link that appears in the upper right-hand corner of your screen, or find the link in the description. Let f be the function defined by f of x equals natural log x over x. What is the absolute maximum value of f? Usually, when we hear the phrase absolute maximum, it means we're going to make a candidates test. But in this case, we cannot make a proper candidates test because we don't have a lower limit and an upper limit. So instead, let's throw this out and let's think about relative extrema. If we wanted to find the locations of the relative maxima, we would make a sign chart of f prime. So let's start with that. First, we need an expression for f prime. This is a quotient, so here comes the quotient rule. Remember, low d high less high d low. Draw the line and down below, the bottom squared will go. When I say low d high, low means the denominator, which is just x. D high means the derivative of the numerator, so that's going to be 1 over x. Less means subtract. Then we have high d low. High means just copy the numerator. D low is the derivative of the denominator, but that's just 1, which I'm just going to erase. Draw the line and down below, the bottom squared will go. Notice that these x's will cancel each other out. So our expression for f prime is 1 minus natural log x over x squared. To make a sign chart, we need the critical values of f. That means we need to find where f prime is equal to 0 and where f prime is undefined. So f prime will equal 0 when the numerator is equal to 0. So 1 minus natural log x must equal 0. Adding natural log x to both sides, we get natural log x is equal to 1. Exponentiating both sides of the equation, all right, drop that base e down, and the base e and the natural log x cancel each other out, so we have x is equal to e. So this is our first critical value. This goes on the sign chart. How about where f prime is undefined? A fraction will be undefined when the denominator is equal to 0. So obviously that means that x will equal 0. Notice that f of x is not defined when x is equal to 0. Natural log x is not defined, and putting 0 in the denominator normally would be a vertical asymptote. So I'm going to put this on the sign chart, but I'm going to put a parenthesis next to it to show that 0 itself is not to be included. Notice that natural log x is not defined for values of x that are less than 0. So this is the end of the sign chart. We cannot go past 0. Now let's decide whether these factors are positive or negative in each interval. If we plug in e right here, so we have natural log of e, that's 1. 1 minus 1 is 0. So right at e, this factor has a value of 0. For values of x that are greater than e, so this is now going to be bigger than 1. So we have 1 minus something that's bigger than 1. So we are going to get a negative value. For values of x that are between 0 and e, natural log of such a number will be less than 1. So when you subtract 1 minus something that's smaller than itself, you are going to get a positive value. So 1 minus natural log x is positive in this interval and negative in this interval. Of course, x squared is positive everywhere because it is squared. So we have this. What about the overall sign of f prime? In the first interval, we have a positive divided by a positive, so that's going to be positive. In the second interval, we have a negative divided by a positive, so that is going to be a negative. The fact that f prime is positive between 0 and e means that f of x is increasing between 0 and e. Because f prime is negative from e to infinity, that means that f of x is decreasing from e to infinity. Since e is the only critical number between 0 and infinity, then e is not just the location of a relative maximum, it is the location of the absolute maximum. Notice that e is not the answer. That's because e is not the absolute max, it is the location of the absolute max. The absolute max will be the value of f at e. In other words, natural log e divided by e. But natural log of e is 1, so we have 1 over e. So the answer is B. If P of t is the size of a population at time t, which of the following differential equations describes the linear growth in size of the population? If the growth of the population is linear, then the derivative of this curve, which will be the slope, is constant. So the answer is A, because this is the only equation which shows a constant rate of change. Let g be the function given by g of x equals x squared times e to the kx, where k is a constant. For what value of k does g have a critical point at x equals 2/3? Critical points of g are where g prime equals 0 or where g prime is undefined. So sounds like we need to find an expression for g prime. This is a product, so let's use the product rule. The product rule says, first time through, we take the derivative of the first factor, which will be 2x, and we leave the second factor alone. So we leave e to the kx, and then we put a plus. The second time through, we leave the first factor alone, so we leave the x squared. But we take the derivative of the second factor. The derivative of e to the something is still e to the something, but there's always the chain rule, so we have to multiply by the derivative of the inner function. The derivative of kx is just k. Notice that there are no values of x that will cause this expression to be undefined, so we can forget about that. So the only critical points of g will be where g prime is equal to 0. And specifically, if we want a critical point at x equals 2/3, then g prime at 2/3 must equal 0. So let's substitute 2/3 in for x and set it equal to 0 and solve. Putting 2/3 in for x, we have this. Simplifying a little bit, we have this. I am noticing that we have a common factor here and here. So let's factor this outside of parentheses. So now we have this. Using the zero product property, we can find solutions by setting each of these two factors equal to 0. However, at a glance, we know that there is no value of k that will cause the first expression to equal 0. There is no exponent that will turn e into 0. That means all we have is the second factor, which could equal 0. So 4/3 plus 4/9 k is equal to 0. Subtracting 4 over 3 from both sides, we have this. We can get k by itself by multiplying both sides by 9 over 4. The negative will survive. The 4's cancel out, so we just have 9 divided by 3, which is 3. So the answer is A. Which of the following is the solution to the differential equation dy dx equals 2 sine x with the initial condition y at pi is equal to 1? Since dy dx is written entirely as a function of x, we can just go ahead and take the integral of both sides of the equation. The integral of dy dx is just y, and the integral of 2 sine x is negative 2 cosine x plus c. Now we will use the initial condition to find the value of c. When x is pi, y is equal to 1. So we have negative 2 cosine pi plus c is equal to 1. But cosine of pi is negative 1. So this is negative 2 times negative 1 plus c is equal to 1. In other words, 2 plus c is equal to 1, and c is equal to negative 1. Let's substitute negative 1 in for c. So the answer is E. Let g be a function with first derivative given by g prime of x equals the integral from 0 to x of e to the negative t squared dt. Which of the following must be true on the interval between 0 and 2? Let us all remember the common case of the second fundamental theorem of calculus. When we have an integral defined function where the lower limit is a constant and the upper limit is just x, the derivative is f of x. Or we should just say whatever the function is right here, that's what it is, but replace the t with the x. So g prime is an integral defined function which does fit the common case for the second fundamental theorem of calculus. So if I take the derivative, of course, instead of g prime, which is what we have now, we are now talking about g double prime. But according to the common case of the second fundamental theorem of calculus, I will just keep the function that we see, but I will write an x instead of a t. That kind of rhymed, bars. So we have negative x squared. So g prime is equal to this. So what can we say about this expression for g double prime? First of all, this is always going to be positive. There is no exponent that you can apply to a base e that will make it 0 or negative. So e to the anything is always going to be a positive value. And if the second derivative is positive, we know that the original function is concave up. We can immediately throw out option B and D because they say concave down, and we just decided that it has to be concave up. We can also throw out option E because if there's a point of inflection, that means it's either going from concave down to concave up or concave up to concave down. But we just decided that the original function g must be concave up everywhere. So there can't be a point of inflection. To narrow it down to the final answer, we need to know if the original function is increasing or decreasing. The original function will be increasing where the derivative is positive and decreasing where the derivative is negative. So let's pick a value between 0 and 2 and plug it in and see what happens. So let's find g prime at 1. So that means the integral from 0 to 1 of e to the negative t squared dt. Problem, I don't actually know how to integrate this. U substitution would fail. The good news is I don't actually need to integrate this. I just need to figure out if this integral is positive or negative. Let's look at a sketch of the graph. Without the negative sign, e to the t squared would be an exponential growth function. With the negative sign, this will be reflected over the y-axis. So this will be an exponential decay function. However, the x-axis is still an asymptote. E to the something can never be 0. So this will stay above the x-axis at all times. So here we are between 0 and 1. So I'm just going to put a 1 right here. The integral of this function between 0 and 1 is the area under the curve between 0 and 1. So I don't actually need to know exactly what that is. All I need to know is that this is positive. See how it's all above the x-axis and we're going from left to right? So this is positive. And if the first derivative is positive, that means that the original function is increasing on that interval. So the answer is A. By the way, I picked the value of 1, but you can see that the same argument would have worked for any value between 0 and 2 because the area is still above the x-axis the whole time. If x plus 2y times dy dx equals 2x minus y, what is the value of the second derivative at the point 3, 0? We can find the second derivative by taking the derivative of the first derivative. So let's get dy dx by itself. Dy dx equals, dividing both sides by x plus 2y, we have 2x minus y over x plus 2y. Now, the second derivative will be the derivative of this. Let's do the quotient rule. Low d high, less high d low. Draw the line and down below, the bottom squared will go. Low d high. When I say low, I mean the denominator. So x plus 2y. When I say d high, I mean the derivative of the numerator. Let's take it term by term. The derivative with respect to x of 2x is 2. The derivative of y is dy dx. So that's low d high less high is the numerator, 2x minus y. And then d low is the derivative of the denominator. The derivative of x is 1, and the derivative of 2y is 2 dy dx. Draw the line and down below, the bottom squared will go. So we have x plus 2y squared. This is an expression for the second derivative. However, right now we basically have three variables. We have x, y, and dy dx. We need to evaluate this expression at the point 3, 0. I know what to do with the x and the y, but what do I do with the dy dx? Well, let's figure out the value of dy dx at the point 3, 0. That's what we should plug in here and here. Evaluating dy dx at the point 3, 0 gives us this expression. But the 0 is gone, so we really just have 2 times 3, which is 6, divided by 3, which is 2. So that is what we will substitute in for dy dx here and here. Simultaneously, let's substitute in 3 for x and 0 for y. So now we have this. All we have to do is simplify. Noticing that 2 minus 2 is 0, and 0 times this is also 0. This term is gone. So we just have to simplify the rest of it. These remaining factors simplify down to negative 6 times 5 over 9, which gives us negative 30 over 9, which reduces to negative 10 over 3. So the answer is A. Last one. For t greater than or equal to 0, the position of a particle moving along the x-axis is given by x of t equals sine t minus cosine t. What is the acceleration of the particle at the point where the velocity is first equal to 0? The velocity function is the derivative of the position function. So the derivative of sine is cosine, and the derivative of cosine is negative sine. The negative is going to change this minus to a plus. So we are now looking at the velocity function. We need to talk about where the velocity is first equal to 0. So let's set this equal to 0 and solve. So that will give us cosine t is equal to negative sine t. This is an interesting case. We need to imagine what value of t will cause cosine and sine to be equal to each other except have opposite sign. Let me take away the negative sign for a second. What value of t will cause cosine and sine to be the same thing? I'm hoping that you memorized every value on this chart a long time ago. Notice that the sine of pi over 4 is radical 2 over 2, and the cosine of pi over 4 is also radical 2 over 2. So, pi over 4 is the value where sine and cosine have the same answer. So cosine is equal to sine at pi over 4. But let's think of pi over 4 as the reference angle. There are 4 places on the unit circle where the reference angle is pi over 4. There's one in every quadrant. The cosine and the sine at any of these locations will be radical 2 over 2, except in some quadrants the cosine will be positive, in other quadrants it'll be negative. Same with sine. It could be positive radical 2 over 2 or negative radical 2 over 2. Remember that on the unit circle, the coordinates x and y are in the form cosine, comma, sine. So the coordinates of this point are radical 2 over 2, comma, radical 2 over 2. In the first quadrant, both coordinates will be positive. In the second quadrant, the x-coordinate, or the cosine, is negative, while the y-coordinate, the sine value, is positive. In the third quadrant, both coordinates are negative. In the fourth quadrant, cosine is positive, while sine is negative. If we wanted the location where cosine is equal to sine, that would be this angle and this angle. However, getting back to the actual problem, we had subtracted sine t from both sides. So we have cosine t is equal to negative sine t. This means that we want cosine and sine to have the same absolute value, but the negative in front of the sine means we want one of them to be positive while the other one is negative. This negative means they have opposite signs. So where will that happen? Here and here. These are the two angles where the cosine and sine have the same absolute value, but they have opposite signs. Remembering that the reference angle is pi over 4, we have 3 pi over 4 and 7 pi over 4. But wait a minute, we want the point where the velocity is first equal to 0. So that will just be the 3 pi over 4. So we have found the time when the velocity is first equal to 0. Now we need to find the acceleration of the particle at this time. The acceleration function will be the derivative of the velocity function, and we have the velocity function right here. So the derivative of cosine is negative sine, and the derivative of sine is cosine. So here is the acceleration function. We just have to evaluate this function at 3 pi over 4. Substituting 3 pi over 4 for t, we have this. Remember that the sine of 3 pi over 4 is positive radical 2 over 2. But then we have this negative sign in the front, so it becomes negative radical 2 over 2. Meanwhile, the cosine of 3 pi over 4 is negative radical 2 over 2. Simplifying, we get negative 2 radical 2 over 2. I'm just keeping the like denominator, and I'm adding the numerator. Negative radical 2 plus another negative radical 2 is negative 2 radical 2. So the acceleration at 3 pi over 4 is negative radical 2. So the answer is A.